Hello everyone and welcome back to the course. In today's lesson, we are going to start learning how to create new sets from other sets. Today's lesson is going to be about operations on sets. In this lesson, we are going to start handling operations such as union, intersection, difference, and symmetric difference. But let us start with the two fundamental ones, union and intersection. Let us consider two sets, A and B, and we define the new set A united with B as the set of all elements X such that X is in A or X is in B. As well, the set A intersection B is the set of all elements X such that X is both in A and B simultaneously. Two important properties about these two operations is that A intersection B is always contained in A or in B. As well, A is always contained in A united with B, no matter the set B. For instance, if we have the set A with elements 1, 2, and 3, and set B with elements 3, 4, and 5, then A united with B will have the elements 1, 2, 3, 4, and 5, whereas A intersection B will have the element 3. Another important operation on sets is the difference between two sets. We say that A difference B will be the set of all elements X such that X is in A but not in B. For example, if we take the aforementioned sets A and B, where A is the set with elements 1, 2, and 3, and B is the set with elements 3, 4, and 5, then A difference B will have the elements 1 and 2. It won't have the element 3 because 3 is an element that is both in A and B. And another important operation on sets is the symmetric difference. We define the symmetric difference between A and B as the union of A difference B and B difference A. Therefore, if we have the sets A with elements 1, 2, and 3, and B the set with elements 3, 4, and 5, the symmetric difference between A and B will have the elements 1, 2, and 4, 5. Now it is time to perform our first mathematical proof. Are you excited, right? In this case, we will show that these two sets are equal. By doing so, we have to show two things: that the first set is contained in the second, and that the second one is contained in the first. If we are able to show these two things, we would have proved that these two sets are equal. Alright, so we will prove the following identity: that the difference between A and B is equal to the difference between A and A intersection B. To prove this, we need to show that the difference between A and B is contained in the difference between A and A intersection B, and as well that the difference between A and A intersection B is contained in the difference between A and B. Let's start by showing the first inclusion. We will prove that the difference between A and B is contained in the difference between A and A intersection B. So let us take an arbitrary element X in the set A difference B. By definition, this means that X is an element in A and X is not an element of B. Now, this element X cannot be in the intersection between A and B because in order to be in the intersection, this element X has to be both in A and B. But we already know that this element X is not in B. Therefore, X is not in the intersection between A and B. Therefore, X is an element that is in A but not in the intersection between A and B. Thus, by definition of difference, we have that X has to be in the difference between A and A intersection B. Now we will show the reverse inclusion, meaning that A difference A intersection B is contained in A difference B. Now, if we take an element X in the difference between A and A intersection B, then this means that X is an element in A, but not an element in A intersection B. Now, if X is not an element in A intersection B, and X is an element in A, for this to happen, X cannot be an element in B, because if X is an element in B and also in A, then X would be an element in the intersection, but this will be a contradiction. So we can conclude that X is an element in A that is not in B, but this is actually the definition of difference between A and B. Thus, X was an element that was taken from the difference between A and A intersection B, and it ended up being as well an element in the difference between A and B. Therefore, the difference between A and A intersection B is contained in the difference between A and B. Thus, as we have shown the two inclusions, we can conclude that indeed the difference between A and B is equal to the difference between A and A intersection B. Another important operation on set that is derived from the difference is the complement of a set. Given a universal set U and a set A that is contained in such a universe, we define the complement of A as the difference between U and A. In other words, this is the set of all elements that do not belong to the set A. For example, if U is the set of all natural numbers and A is the set of all even numbers, then the complement of A will be all of those numbers that are not even. Therefore, the complement of A is the set of odd numbers. Something that you will notice in the next lesson is that set operations and logical connectives share similar rules, and this is going to facilitate the way that we operate sets. And there you had it, set operations and properties in action. In the next lesson, you will learn some important properties of all of these set operations. See you in the next lesson.